what I was mentioning before I was so rudely interrupted by the timer is that glass is actually a supercooled liquid. Okay, it appears solid, but it lacks a crystalline structure, and so it's not a rapidly cooled solid. It's not. It's a supercooled liquid. As a matter of fact, if you look at the glass in window frames from houses that are 50 years old or so, you will find that the top part of it is actually thinner than the bottom part because there has been some flow of that glass down into the lower part. It's small, but it's something that you would have a scientist would distinguish. Not you will look at it and you say, yes, that's solid, but the scientific definition of it would be a supercooled liquid. And fortunately, it is that way because we can then look out through it and keep the bugs out. Minerals can be formed at high temperatures. There's the Bowen reaction series, which is silicate crystallization sequence. Ferromagnetic silicate crystallize at higher temperature, and minerals crystallizing later are progressively richer in silicon. Okay, and so it goes through the different series, and we can duplicate that when in the laboratory by making them in a particular sequence. Okay, whether something actually happened that way or not, that is open to conjecture, but we can do certain things in the laboratory to get these materials from those other ones. Some minerals are formed at normal temperatures. Earth's surface in contact with oxygen, carbon dioxide, and water will form carbonates, sulfates, oxides, and these other materials. Okay? Except for oxides, they have specifically lower hardness and specific gravities than minerals formed at higher temperatures. So when something comes out of a volcano, it's going to be a lot harder and have a bit higher density as well. Altered minerals. These are exposed to different environmental pressure changes, temperature, chemical solutions. You can change one mineral into another. For example, rust, right? We've all seen that reaction take place. And this occurs over 150 degrees and 2,000 atmospheres of pressure. Garnet, epidote, talc, graphite, and serpentine as a source of asbestos, back when people wanted a source of asbestos, can be generated in that manner. Okay, but just at a lower temperature, you have some changes that can take place as well. Ore minerals are mineral deposits with economic value. These are often found in veins, thin, flat bodies of mineral material, left over from crystallizing magma flushed away in hot waters. Pyrite, that's the iron sulfide that I mentioned is fool's gold, and chalcopyrite, which is sulfide of copper and iron, and there are other ones as well. Aggregation of more minerals, and perhaps together, minerals are physically combined to make rocks, and that can happen, sorry about that, on how rocks are formed: igneous, sedimentary, and metamorphic. Igneous means right out of the volcano. Sedimentary means that it's been settled for a while. Metamorphic means that it's between the different ones. So igneous rocks are formed from magma below or above or below the Earth's surface. All rocks were at one time igneous. Maybe. I don't know. That's a speculation on their part. Cooling rate determines the texture. Intrusive igneous rocks are formed beneath the surface. Slow cooling process creates large crystals, coarse grained. The extrusive igneous rocks, these are formed from lava on the surface. Rapid cooling produces small crystals. And these are the ones that usually have more pock-marked structure in them. This right here would be a coarse-grained, slow cooling, producing these large ones. The ones that you get from the volcanic eruption or the lava tubes usually have a lot of holes in them, and that's because the hot gases are venting out through those holes. And the rock classification are based upon the mineral composition and the texture. Non-ferrous, okay, is on the left side of this figure over here. These are low in density and light in color, and granite is the most common example. I know you don't think of these as low in density, but granite is compared to some of these other ones. These ferromagnetic ones are greater in density, darker color. An example here would be basalt. Okay, right there. So you can see how here's quartz down here, granite up here. So you have difference right here in terms of the grain. Quartz is fine grained, granite is coarse grained. Okay, and then you have the difference in this way in terms of 75% silica, and this is only 45% silica right here. This is increasing potassium oxide and sodium oxide, and then increasing calcium, iron, and magnesium oxide going in this direction. So you can see it's a composition of, first of all, silica in all of them, and then these other materials, and either increasing this way or increasing this way, depending upon what the concentration is. But nevertheless, it's still almost half silica throughout everything. These are sedimentary rocks, and these are formed by particles dissolving from previously existing rocks. It's accumulation of silt, sand, other materials. They settle out of water, and then other things crush them down or have that pressure on top of them. So they accumulate and form that. The initial silt is really, really small, and if you try to step on it, or even clay dust when it's wet, you sink up into your knees. Sand actually is a larger size than clay. It's just that sand allows water to go through it more rapidly, and clay just sort of lets it come together and harden, and then forms a structure that is very resistant in one direction. Of course, you can slide along it extremely well. I've done some, when you're talking about mudslides and all that, it's usually some basis of clay that's involved in that. We had tubes in Hawaii we used to slide down that were essentially never could get the stains back out of the shorts after we did that. And then this right here is based upon the sediment type, clastic, these three right here, and chemical, right? Sediment type. And this is a conglomerate, sandstone, siltstone, claystone, shale, okay? Limestone, dolomite, gypsum, and salt. So these are sedimentary rocks, okay? These are chemical sediments formed from dissolved rocks and minerals, and they have three sediment paths: chemical precipitation from solution, crystallization from evaporating water, and biological sediments. And here is the different classes as well. This is essentially a blow-up of that table on the other side with the particular rock name over here, okay? And here you have them again, where you are looking at the same things. This should look very familiar to you. You see a lot of this as you drive along the highways here in the Ozarks, because we had to chew through this in order to level out some of the roads. And this right here, you can see the streaking that is from the different layers, and this usually happens after an ocean or something like that, or a riverbed is dried up. You get this type of compaction taking place. Lithification is the rock formation that takes place from compaction first, reduces the thickness of the deposit and squeezes out the water. Then cementation. Spaces between the sediment particles are filled with chemical deposit. The chemical deposits bind the particles together. This is a natural type of cement that takes place. And you can see some of that take place in some of our rocks around here. We have that as well. Okay, so it's after, this is how it looks initially, made up of these types of materials. You've got pore space in there. Some overburden, heavy weight, stepping on it, somebody jumping up and down, crushes it closer together. And then you can have a chemical reaction taking place with carbonates and other ones that would form essentially a natural type of cement. Metamorphic rocks are previously existing rocks changed by heat, pressure, and rock solutions into a distinctly different rock. Movement of a crust, heating of hot solutions, temperature must be high enough to cause recrystallization, but not melting. Okay, so shale goes to slate, goes to schist, goes to gneiss, to granite. That is how you get from shale to granite. Okay, limestone can become marble, sandstone become quartzite, igneous rock can become schist to gneiss, to granite. Okay, so there's different ways in which metamorphic rock can be formed. Foliation is the alignment of flat crystal flakes into sheets. Foliation just means that you're making a folio out of it. It comes from some of the words for paper, right? So that each one of those is flat paper crystal flake sheets. Pressure upon it, rock cleaves along the planes and where the grains are aligned. Okay. Non-foliated parent rock consists of one mineral. The grains are not aligned into sheets. Non-foliated, down here, they should have flipped these, shouldn't they? Are the quartzite and marble. And then you have slate, very finely foliated. And then finely foliated. And then coarsely foliated. And I would have had this non-foliated down here. So it goes from slate to schist to gneiss. And then you've got your quartzite and your marble. And these are some examples of them. And you can see the streaking and all of that takes place on them. Here's what they call the rock cycle, going from one type of rock to another rock. And they're talking about moving continents and seas advancing and retreating, weathered and eroded by wind and rain. All these things can cause changes to occur between different types of rocks. Okay, and that's the end of that chapter. The next chapter is on plate tectonics. And this is a fairly short chapter. It's just going to talk about what is a plate. The idea, and we know that there are all sorts of different plates pushing and pulling underneath the surface of the earth. And we have the ring of fire along the California coast and on the east coast of the Orient. That forms a whole circle of where we have active volcanoes and a lot of other activities. And this right here talks about possible ways of things that could have been a long time before. Okay, right now we have the North American right here and the South American here. Okay, and then we have this ring around here and down through here, which is where a lot of the active volcanoes are, and as a result of some of this. And some of it's going up in through here as well for your volcanic activity. And what they've done is they've tried to divide the earth into different planes, because they talk about what happens at the interface between different planes, where one is buckling up against the other, causing mountains to rise or volcanoes to erupt. And we see evidence of this through Earth's magnetic field, the gravity effects, the heat flow, and the vibrations in the Earth. Vibrations in the Earth, also known as earthquakes. These are seismic waves, and we're going to have to stop for there.